Okay, so we are going to now do a summary of the disc, washer, and shell methods. So in this video, we will compare the formulas and setups of these methods, and then we'll also compare examples. And for the sake of time, because I'm going to do a ton of examples, I'm just going to set up the examples and I'm going to assume that you know how to integrate. So, okay, keys for volume problems. You want to always have just like a basic sketch of the region and a basic sketch of the revolution. Now, they don't have to be perfect, but you do need some relevant info and you just need something to kind of go with. You also want to decide which formula and variables are appropriate. So take a second to think about that. So disc, washer, shell method, that's going to be important when they all start coming together. And then you also want to label the revolution in ways that will help you fill in your formula. So the revolution is super important for like having that picture is super important to help you fill in the formula. And then of course, then you finish your formula and you integrate. So, okay, let's review all the formulas. And if you are using this to study for a test, I strongly recommend that you write these down. In fact, I have guided notes that accompany this. So if you go to divideandconquermath.com and go to the Calc 2 section, you will find my summary of this topic. I have notes that you can just use. I think that those are super clutch for this video. So I would say just download those and use those, but write these down if you are trying to study for an exam. Okay, so first let's talk disc and washer method, which are kind of similar. So the disc method, so if you go about the x-axis, so everything's going to be in terms of x, and you just got whatever your radius is squared times pi, so it's like pi r squared, but your radius is changing. Versus for your y-axis, it's going to be pi, and then it's going to be like a y squared formula. So around the x-axis, everything's in terms of x. Around the y-axis, everything's in terms of y. And of course, if we want to remember, like, why would that be true? So if I have, say, like this region here, and I want to revolve it into this solid, so think about what the cross sections here look like. The cross sections are circles. And so what integration is doing is it's like finding the area of each one of those circles. And we know that the area of a circle is, of course, pi r squared. But as you can see, as I move up and down the solid, right, these circles, they're all going to have different radiuses. But the beauty of integration is that it will take each one of these little slices. It can take an infinite number of these slices, right? And so we'll basically be calculating this pi r squared formula for each one of these slices. But what integration does is that it does that on that like infinite scale, because integration is ultimately just an infinite sum, or it's a Riemann sum. And so that's why it will just sum up all of these pieces. Now, the washer method is very similar, except now we're subtracting an outer radius versus an inner radius. So if we go about the x-axis, I have the outer radius squared minus the inner radius squared, of course, times pi. And if we go about the y-axis, then everything's in terms of the y-axis. And you can pause this video if you want to write this stuff down. So again, if we just want to know why is that the case. So if I were to rotate this region about this x-axis, and then you see now I have a big hole, right? Because the solid just is going to create this big hole. So what does the cross section look like in this case? So if I just take this slice at this little cross section, so there's my hole. So I have this outer circle and this inner circle. So we have the outer ring. So that's going to be this outer part here. And then for the inner part of the hole, so that's going to be defined by this part here. But when I take the cross section by itself is just going to look like its own little, it's going to look like just a circle with a hole in it. And so then, like, why does this formula work? So I have my outer circle, which is going to be computed pi r squared, but then I'm going to subtract whatever that the area of the inner circles is, which will be pi little r squared. So if I subtract those, then I will get this pi r squared minus little pi r squared. It'll just leave me with the ring here, which is all that I've got, right? So that's the intuition behind that formula. So when would you use the washer method instead of the disc method? So it's really when the revolution is not this like perfect solid. So I think of it as either has like a clear hole or some sort of like little divot in it, okay? So how can you be sure if your revolution is solid or has a hole? You have to draw the beep revolution, okay? You have to draw this, okay? If you don't draw this, then you are really gonna struggle with all of this, okay? So, okay, let's keep going with this. With the disc and washer method, when do you integrate with respect to x? So it's really when you rotate or revolve about the x-axis or anything that is parallel to that, okay? Versus with the disc and washer method, when do you integrate with respect to y? So it's when you revolve about y or anything that is parallel to y. And so then sometimes we have to make additional adjustments to the radius. So those adjustments are when we revolve about a line, so not just the x-axis or the y-axis. Then we make like additional adjustments to that radius. So really, anytime you aren't just strictly revolving about the x-axis or the y-axis, then we make like a slightly more complicated radius calculation, okay? So let's now talk about the shell method. So the shell method has kind of a different vibe to it, I guess we could say. So for the shell method, so if I am using this about a vertical line, so the y-axis or something parallel to that, so look at how this formula is different now. So now I've gone around the y-axis, but the formula here is 2 pi, and then I take the shell radius times the shell height, but all of this is in terms of x, okay? So if we wanted to like think about this, oh, let's just compare that first just to the x-axis, sorry. So if we are now doing this about a horizontal line, say the x-axis or something parallel to that, so it's still the same idea. So you've got 2 pi times your shell radius times your shell height. So the only thing is, okay, with height, so really it's more like width. It depends on how you want to think about this. So I think a lot of times when I go about a horizontal line, I have a tendency to think of this really as width, but depending on which way you orient yourself with the picture, you could think of it either way, right? But okay, so this is a difference because now everything is going to be integrated with respect to y. So when we're talking shell method, it kind of works the opposite from, say, like the disc and the washer method. Okay, so the shell method is not using cross sections, okay? It's literally using cylindrical shells. So that is like why there's a difference with these formulas. So think of these as like thin tubes, okay? So here is a tube. And so if I were to unroll that specific tube, so if I wanted to figure out what the volume of this like little tube was, so the volume of this would be, so it's got this circular part. So usually when things are circular, then we're involving pi, but the rest of this will be 2 radius times the height. So where does that all come from? So the radius comes from, so you have to kind of wrap your head around this, right? So the radius of this shape here is calculated from here to out here. So how does that translate when I unroll? When I unroll this, here's my same part on the radius from here to here. This is why we need to do 2 times the radius, right? So it's not enough. And then, of course, then we'll have, and then we'll have, then we'll have the height. So the height is still the height even when you unroll it. So we need 2 times the radius to get this whole length, then the height, and then pi because it's circular, okay? All right, so let's talk about now how that translates when we're talking about a revolution. So I've got this shape here, and so I rotate it around to make my little bundt cake. Cake. And so, all right. So the thing here is it's a different way of calculating the volume. So how does my shell fit in here? You could think of, so what I'm going to do is I take like my tiny little sheets of paper and I just start rolling one of those shells inside another like this. So here is one shell wrapped inside. And I just keep wrapping one shell within another shell. So I have all these shells kind of caked inside of here. And so the beauty, again, of integration is integration allows us to do this an infinite amount of times. So it's now not slices that we're dealing with. It is shells because of the nature of how we set up the formula, but it's still going to be an infinite amount of them. So with the shell method, when do you integrate with respect to x? So again, you integrate when you are revolving about a vertical line. So it kind of works the opposite of that disk and washer method. So this is when you're revolving either about the y-axis or x equals L, something of that form. Versus with the shell method, when do you integrate with respect to y? So this is when you are revolving about a horizontal line. So that would be either the x-axis or y equals k. Okay, so if you rotate around the x-axis, what is the shell radius in that case? The shell radius, it is just going to be y, so there's no adjustment needed. So when you just rotate about a normal axis, then you don't have to, like the radius is just y by itself. And if you rotate about the y-axis, then your shell radius will just be x. There's no adjustment needed. Okay. But when do you need to make that adjustment with subtraction to the radius? So once again, when we rotate around any line, either x equals L or y equals k, that's when we start making little adjustments to how we think about our radius, all right? So if you need to use subtraction to find the radius, then how do you do this? So you want to treat the radius as any other length. So in general, when you're doing that, so if you just think about like, why does this work the way that it does? So if we just think about determining lengths from basic algebra, so when I determine the length of, say, this line segment from A to B, so how do I do that? I take whatever B is, and then I subtract A. So I always take that highest value minus that lowest value. If my line segment was set up like this, how would I find the length of this line segment? I'm assuming that D is the higher value, so I always take the highest value minus the lowest value. So this is the same concept that we're using with the radius. It's always that highest minus lowest value. And this is effectively what a radius will be, right? So depending on which axis that you've rotated around, we're effectively just either trying to find this length of this radius or this length of this radius, whichever way you've rotated around. So it's kind of the same idea. Okay. One other thing, radius is always calculated using your initial region. So you need that anchoring picture of like what your region looks like. So wherever that region started, when you start making calculations, it is always going to be from that starting point. Okay, so with the disk, washer, or shell method integrating with respect to x, how would you find your limits of integration? So with all of these, so I know that, so now we're just talking about when you are literally integrating with respect to x. So I know that these are different situations of what we're revolving about, but just in general, when you are integrating with respect to x, how do you find those limits of integration? So you look at kind of that initial picture that you drew, and you look for your highest and lowest x values of that region that you drew. And if you are integrating now with respect to y, so if we're integrating with respect to y, how do you find your limits of integration? Same idea. You just look for your highest and lowest y values of your region. Okay, so again, the key to these problems is drawing the revolution and then labeling it appropriately. Now, if you feel sketchy about drawing your revolutions, you do need to address that anxiety. Sometimes I feel like people don't want to draw the revolutions because they're like, oh, my picture's not good enough. It's literally just something for you to reference. So if you are finding that you are hesitant to do that, I strongly recommend that you watch my video on just some advice on that, but they don't have to be perfect. You just need that reference, okay? But you have to do this or you are really going to struggle with this. So like I said, I have a video where I only do the sketching. And so go watch that first before you finish this video because you can't resist sketching and watch the rest of this video. You're going to have to be able to do it. Okay, so now I'm going to show you 12 setups of these types of problems so that you can really wrap your head around these different methods, okay? So I'm only going to set up the integral to save time. I'm going to skip solving it. And we will use the region bounded by these curves. So y equals 3x, y equals 0, x equals 1. So this is the region that I'm going to use, okay? All right, so I've got this region. So the first thing that you want to do, like I said, is you need to know what does this initial region look like. So when I sketch it out, here's my 3x, here's my 1, here's my y equals 0. So this is what my region looks like, and I do want to kind of keep that in mind. The other thing that I want to keep in mind is I want to keep in mind what the points of intersection are. What I'm really interested in are what are my highest and lowest X and Y values. So by sketching this out, like I said, it doesn't have to be perfect, but at least knowing what your points of intersection are and knowing what's on top, what's left, what's right, all that good stuff, this is going to really help you out a ton. Okay, so now let's do this. So we are going to revolve this region about the x-axis using either the disc or washer method. So I need to start with that initial region, and then I'm going to rotate it or revolve it about the x-axis. So it looks something like this. So there's my shape, and I can see that it is a solid. So my cross section will look like this, right? So if you're not sure if it's a solid or not, think about what the cross section will look like. My cross section is just going to be a circle. And so since it's a solid, of course, that means I'm going to use the disc method, okay? So solids are disc method. All right, so now I have to think about what is the radius in this situation. And so this is why having that revolution is so important. And I want you to notice that when I think about my radius, what I'm thinking about is I'm doing my radius off of that initial starting point. So this is the side right up here. This is the side that I started with. So when I think about my radius, I think about starting from here and going down, okay? So the radius is also dynamically changing with the curve. So this is another thing that you want to pay attention to. If you get confused by this, you can always draw a few radii. And as you can see, bigger, smaller, smaller, even smaller. So we can have a radius that works like this. And so of course, this line here is the line y equals 3x. So y equals 3x is what is dictating what the length of that radius is, okay? All right, so now we can start thinking about our integral. So like I said, the whole point of having kind of this piece labeled is, so I've rotated about the x-axis, I've revolved about the x-axis, so everything's gonna be in terms of x. So when I look at this drawing, I am just looking at my x coordinates, and I'm looking for the highest and the lowest because that is what I'm going to use for my limits of integration. So my limits of integration go from 0 to 1. And then I need to set up the rest of this. So for the disc method, I'm going to have, oops, I forgot my pi here. Okay, there it is. So I've got my pi r squared, but of course my r is this dynamically changing formula. So what will be my r of x will be this, let's see. It will be this 3x squared, okay? So here is the setup, and so of course now if I go with the rest of this, so I've got my pi's everywhere in here, and so this will just be integrating pi from 0 to 1 of 9x squared dx, and then you can finish the integral. So again, I'm just setting these up, okay? All right, cool. So now we're going to revolve this about the y-axis, okay? So I've still got my drawing here just to kind of help level everything. First things first is we have to draw what does this revolution look like. So I'm gonna revolve this way. So my revolution looks like this. So it has this hole kind of going through it, okay? And so once again, so if you're not sure, if you're supposed to use the disc or washer method, so if I just take a cross section here, what does that look like? It is something circular, but I can see right through here, right? There is definitely a hole in this. So, okay, so I'm definitely going to be using the washer method, right? So my washer method is set up like this. And I also want you to notice that in setting up this formula, so I've revolved about the y-axis. So that tells me everything has to now be in terms of y, right? So I want to make sure that I'm respecting that before I go much farther. The other thing is, now everything has to be changed in terms of y, right? So I have this function in terms of x, and now I need to switch it so that it's all in terms of y. So that is something that we'll work on in a second, but let's think about our outer radius versus our inner radius. So my outer radius is really being created by this wall right here. And my inner radius is being created by this kind of sloping part in here. So you want to just kind of level set those things. And remember, this is where I started. So when I'm doing my analysis, it's where did that revolution originate from? Okay, cool. So this is the line. Remember, this is the line x equals 1. So that's going to help us get to our radius, our outer radius. And this part in here, this is the line y equals 3x. I'm going to change y equals 3x to x equals y over 3. So I'm going to just flip all of that. And so now I should have everything that I really need to kind of get this party going. The other thing that I need to pay attention to now is, so since we're doing everything in terms of y, I now need to pay attention to what are the highest and lowest y coordinates in this situation. So now I've got all those pieces. I've identified my outer radius, my inner radius, my highest and lowest y values. I've got everything in terms of y. We are ready to go. Okay, so the way that this is going to get set up is I've got from 0 to 3, 1 squared minus y over 3 squared. And so, of course, then I can just keep moving forward with this. And that's going to be the setup for the integral. And then you keep going with that. Okay, cool. So now let's rotate about the line x equals -1. Okay, so now we're getting into weird rotations where we know that we're going to have to make more adjustments to the radius. So here is where -1 is. So I need my revolution to go about this way. So I really just try to draw a reflection. So again, like, don't stress yourself out about having this like perfect sketch. My triangles do not look perfectly symmetric. It's just something there to kind of set my expectations right. And so this is good enough for what I need. And now I can make my little revolution here. So I've clearly got this like giant hole in everything. So since I have this big hole, I know that I'm going to now use my washer method. Now, I've also rotated this about the line x equals -1. That is parallel to the y-axis. And so because of that, boom, there you go. So everything is going to be in terms of y, and like I said, we're using the washer method. So since I've got, so that I can account for that big hole in everything. All right, cool. So also the other thing I want to just remind you of now is, so where do we measure that radius to? So specifically what I mean is, should my radius calculation, should it be going from here to here, or should it be going from here to here? So I actually want you to come up with your what you think about this before I tell you. So if you have to pause and think about it for a second, feel free to. So my radius needs to always go from the initial region to the radius. So remember, this is where the initial region started. So I need to start from here and then move into the center, okay? So this is where we want to start. If you don't remember that, you're going to screw the whole calculation up and go in the wrong order. So you just want to make sure that you're doing that. And so we started here, we went that way. So this is where all of our information needs to come from. So notice now how I'm thinking about my outer versus my inner radius. My outer radius just has this giant wall right here. So my outer radius is just going to be a number. But as you can see from my inner radius, so depending on where I am, so it's going down this slope to this center line in here. So there's going to be this difference. Okay, and remember, you always go from the highest to the lowest. So I mentioned that sometimes I get confused with left and right. I don't know what is with me, but this is just like this pervasive problem I've had my whole life with left and right. So it's a lot easier for me to think of highest versus lowest. So looking at this, I know the higher values over here and the lower values are over here. So, okay, I need to now do all my calculations with that in mind. So for my outer radius, what is this line? This is the line 1, and then I need to subtract off what this line is. So also just keep it straight, you're subtracting, so you're finding this difference. This is 1 minus -1, so that becomes 1 plus 1, so that equals 2, okay? So my outer radius is a total length of 2. And that makes total sense, right? So like also like if you're, sometimes people get a little confused with like finding the length, but look at your picture, right? You can tell here's 1 unit, here's a second unit. So it should definitely be an outer radius of 2. So make sure that it makes sense. And then for my inner radius, so again, here's my higher value. So my inner radius is this changing line of y over 3 minus -1. So my inner radius is going to be y over 3 plus 1. so there's what I'm going to plug into my formula, as you can see, and then you can just kind of keep going from here. So you have to FOIL stuff out. There's more work to do. For the sake of time, I'm going to skip over that because we have a lot of examples to get through. So now we're going to revolve about the line x equals 2. So you should try this now. We've talked about enough of these. I think you can set up the integral from start to finish. So draw the revolution, all that good stuff. Let's check in on how you're doing. Worst that happens is you get it wrong. Hit play when you've got it. Okay, so here's my revolution. So x equals 2 is going to be somewhere to the right of this initial region. So here's where my x equals 2 is. So my revolution looks something like this, okay? So obviously I have a giant hole again, and I have rotated around something that is parallel to the y-axis. Therefore, I am going to use the washer method, and everything has to be in terms of y. So I've got kind of my expectation ready to go, and now we can start finding our outer and our inner radius. Okay, and the other thing you want to remember, right, so this is the thing that can kind of get you if you're not thinking about it, this is my initial region. This is where everything is going from, okay? So I just want to make sure that when I'm calculating my outer and my inner, that I'm doing the calculations from this part. So when I find my outer radius, I'm going from the center here. Here's where my outer radius is now, right? And remember, we're going from highest values to lowest values. So in this case, the center is higher than where this outer radius is. So for my outer radius, this line here is 2, and this here is y over 3. So there's my outer radius. Versus my inner radius, so it's going to be this constant, right? It's just this wall. But again, the higher value is, in this case, here to here. So that's 2 minus 1. So there's my inner radius. So I can plug all of that in, bada bing, bada boom, and then, you can just finish it. So this is the integral for that one. Whew. All right, so now let's keep going. Okay, so now we're going to revolve about the line y equals 5. All right, so now the line y equals 5 is going to be above my solid, right? So here is kind of a loose sketch. So I've got my triangle, here's the line y equals 5. So I literally just take this and I just fold it over and I reflect it. So I kind of draw that, and if I fill it all in, so now I can see what my solid looks like, and I've got this giant hole. So this is a horizontal axis. It is parallel to the x-axis. So my friends, now we are integrating with respect to x, right? So everything now is set up in terms of x. So I declare that before I go any further. So I hope like you're kind of getting from this, like set up that solid, and then once you kind of figure out what you're rotating with respect to, like make sure you declare that variable so that you don't, choose the wrong thing. Okay, now let's keep going. Now we can discuss, so how should we be doing our calculations? So remember, this is the initial region that I started from. So this is where all of my calculations for outer versus inner radius needs to happen. So when I talk about my outer radius, so I'm going from the center to where the outer radius is. This is the top part of that calculation, and this is the bottom part of that calculation. So that's going to be 5 minus 0. So that's going to be an outer radius of 5 in this case. And for my inner radius, so again, I'm going from that center part to here. So that's going to be 5 minus, remember everything's now in terms of x, so it's going to be 5 minus 3x. So I get to go back to using that 3x calculation. So there's everything for my inner radius calculation. And then also remember everything's in terms of x. So also the other thing that I just want to remember is that I'm now choosing my highest and lowest x values from this region up here. So we just plug everything in. There you go. There's still more work to do, but like I said, the whole point of this is just to set up the calculations, so we're good to go. So this one is done. Okay, and now we're going to revolve about the line y equals -2. So again, if you feel like you're getting this, I think you should pause here and just try this one on your own, and then hit play when you're ready. Okay, so y equals -2 falls below this region. So here's my solid, okay? So here's my solid, and so since I'm rotating about something that is parallel to the x-axis, I set up everything in terms of x, and then remember, this is where my initial region starts from. So this is how all my calculations, like when I'm coming up with my outer and my inner radius, this is what I'm using for my top and bottom calculations. So for my outer radius, so now I'm using this line here going down to the center. Here's the top, here's the bottom. So for my outer radius, this is 3x and this is -2. So 3x minus -2 will give me 3x plus 2. And then for my inner radius, so now it's just this solid. So this is the line 0, and then this is minus -2, so my inner radius is +2. Okay, cool. So now we can set everything up again. I've got my outer radius, my inner radius, and then once again, I'm going from 0 to 1, bada bing, bada boom. We're all good to go here. Okay, so we've done all the disc and washer method. Now we're going to talk about the shell method. So we're going to redo everything with this with the shell method. Good times. Okay, so now we're going to rotate this about the x-axis, but since it's now the shell method, when I rotate about the x-axis, things are going to change, right? So it's shells, and so first I do want to get that rotation. So there's my solid in this case, okay? But now it's just a slightly different way of thinking about everything. So since it's shells, and I rotate it about the x-axis, everything has to now be in terms of y, right? So I have everything kind of here. So I have 2 pi, my shell radius, and my shell height. And remember, height is, sometimes that can be a little weird, but in this case, that's, I guess, straightforward. Anyways, so I've got everything in terms of y. That's the big thing that I kind of want to impress upon to myself. Now, we're rotating about the x-axis, so that's going to make things a little bit easier, right? So since we go around the x-axis, there's no adjustments that we need to make to the radius. So that part makes our lives a little bit easier. So our radius in this case, remember, everything's in terms of y. So my radius is just going to be y. So I don't have to worry about that part. And then for my shell height, okay, I call this height, but it's like sideways height. So again, it's kind of like how you orient yourself. We could also call it width. You have to decide what terms you like. I still think of it as just height, but I just kind of rotate the way that I'm thinking about things. Anyways, my height is being dictated this direction here, okay? So these are the lengths that I have to be able to, describe. And so remember, in describing this length, how do we do that? Your highest value minus your lowest value, right? So that's going to be kind of our rubric for this. So this length here we know is 1. This length here, so putting everything in terms of y, is y over 3. So there is everything that you need to know, okay? All right. So now we will find the volume for generated about the y-axis. So now that we're going about the y-axis using still the shell method, now everything's going to be in terms of x. So here's my shape again. So there's how everything's revolved. But now since I'm revolving about the y-axis, so everything now needs to be in terms of x. Okay, cool. So I have my shell radius and my shell height. But since we've revolved about the y-axis, it is going to keep things easier. So my shell radius will just be x. So since there's no adjustments needed, so that part's not so bad. My shell height goes this way. So now I'm figuring out what is this dynamically changing height, but I'm taking that highest minus lowest value. So in this case, that's going to be 3x minus 0. I know I didn't need the 0, but I like to throw it in there just so that you kind of have that sense of calculating what that height is. Okay, so yeah, but we could ultimately drop the 0. Bada bing, bada boom, integrate, you're all good to go. Okay, next up. Now let's talk about revolving about the line x equals -1. So I've already got my solid drawn here. I feel like we kind of know which way we need to go with this. Okay, but now we have to kind of keep everything straight. So I'm revolving about x equals -1. So that is something that is parallel to the y-axis. So that means that I am integrating with respect to x, right? Okay, cool. So I am integrating everything with respect to x. And so now when I think about what that radius calculation is, so how is that radius being calculated? The radius now is going from like this length here to this -1. So I have to do this calculation. So it's whatever my x values are here, but then, so it's whatever these x values are, but then we also have to have this adjustment for this. So to calculate this length, it's whatever my x value is minus -1. So here's my radius, x minus -1. So it's always going to start with an x or a y, but when you adjust it, you just adjust for whatever the appropriate direction is. Now the other thing here though, right, is so since we're going this direction, I'm going from highest to lowest. This is the side that's going to be the highest, whatever the x value is, and the lowest will be -1. So here's everything that kind of goes into that. And of course, then I can just turn that into +1, so I'll make that a +1. And now let's discuss, so what's the height in this case? So now for my height, so my height is going to be going from here to here. So again, we're going from that highest to lowest. And so that's going to be 3x minus 0. And again, we can just call that 3x. So we don't have to really adjust that or do anything too crazy there. Okay, so my question is then, so now I want to revolve this about the line x equals 2. So if I go about x equals 2, how does that change things? So I would recommend that you pause here and you give that a try, just to check in on how you're doing, and then hit play when you're ready. Okay, so I've got my revolution, so there it is. So my x equals 2 is going to be over here. So remember, this is the initial region that we're starting with, so all of our calculations need to go there. Okay, so since I'm still revolving about something that is parallel to the y-axis, I've got this situation here. Everything's going to be in terms of x. But since now I'm revolving about x equals 2, I know that there's going to be also an adjustment to my radius. So my radius now is going from here to somewhere out here, right? So wherever my x is, so where does this radius end? It doesn't matter, but what's the starting point? So if I'm trying to just find whatever this length is, the highest value is here, which is the value x equals 2. So now in this case, we're going to minus whatever that x value is. So that's the subtle difference, right? If we go back to the previous example here, so this radius, so started highest to lowest, so somewhere in the region to here, here my x value would have been the highest and my center would have been the lowest. But in this case, now my center starts at the highest point and my x value starts as the lowest. Okay, cool. And then we need to get our height. So the height is still going to be the same, right? So the height is just going to be dictated by this is 3x, so we're good to go. All right, so now, of course, we're going to now do everything. We're going to change the orientation. So now we're going to revolve about the y-axis, or sorry, not about the y-axis, about the line y equals 5. So I would actually challenge you at this point, like we're almost through all of our examples. So I would challenge you to just do this one on your own, and let's just check in on how you're doing. So pause here, give it a try. So here's my revolution. So there's my solid, so I can see everything here. And okay, so since I am now rotating about something that is parallel to the x-axis, what does that mean? That means that I'm going to integrate with respect to y, okay? And then my radius is going to be calculated this way, right? So obviously I have to make an adjustment to my radius because I'm not rotating about just a normal axis. So here's how my radius is structured, and I can see here 5 will be the highest point, and then whatever x value I have will be the lowest point. So my radius will be 5 minus, or sorry, I said x, I meant y, because everything needs to be in terms of y. So 5 minus y, so there's my radius, okay? And then for my height, again, now we're going the other way. It's height or width or whichever way you want to think about it. But my height, more like width, is going to be calculated going this way. So remember, again, highest to lowest values, but now we're going voop, voop, voop this way. So highest is over here, lowest is over here. So what does that mean? This line here is the line 1. This line here is y over 3. Again, we had to change everything to be in terms of y over 3. So 1 minus y over 3, boom, there you go. There's everything all set up, okay? Cool. And now we have one more. So now we're going to revolve about the line y equals -2. Again, I think you should pause, give this a go, make sure you've got it, and then hit play when you're ready. Okay, so last time where we have to remember, where did we start? We started here and we're revolving about something down here, okay? So here's my line y equals -2. Obviously, that is parallel to the x-axis, so I'm going to set up an integral that is all in terms of y. And so now we have to figure out what's the shell radius. Okay, so for the radius, now I'm going somewhere up here to down here. So this is starting with, this means that my y value will be the higher value, and the center will be the lower value. So that's going to be y minus -2, which of course will become y plus 2. And then we can work on this shell width. I'm just calling it width at this point. So for my width, so my widths are going this way, very similar to the other calculations that we had. So it's that 1 minus y over 3. That's going to get me to my width. Woo! All right. If this was helpful, I would love it if you hit that like button. This was definitely a labor of love to create this one. So just getting a like to know that it was helpful would be really motivating and nice for me. Also, leaving a comment would be fantastic, or subscribing to the channel. I drop lots and lots of content on Calc 2 and all sorts of other topics. So yeah, thanks for watching. And I think I need to take a break. I will talk to you.